Good morning, everyone. I'm Sharafat from Vienna, and I would like to welcome you to our third day of the workshop. Today we will continue discussions on data processing, and our first presentation, introduction to Madoka and Madoka data processing demo, will be made by Dinesh Manandar from the University of Tokyo. Dinesh, the floor is yours.
Okay, can you see my PowerPoint slide?
Yes, thanks, Dinesh.
Okay. So how about the audio? Is it okay?
Now it's okay from my side.
Okay.
Hope everybody can hear you.
Okay. So today, sometimes it may be a little bit noisy because I'm at home today, and in our apartment, another room has some maintenance work, so I'm sorry for that. Anyway, so let's start and welcome everybody to this last day of our training. And today I will be introducing you about the Madoka. So this is about the PPP. So I will introduce about this Madoka Ppp system that we have, and also some hardware and software. And also we distribute this hardware and software to some of the universities or some organization, research institute based on the collaboration activities that we have. It's not just a freely distribution, but we need to have some collaboration on that. So based on that, we provide the hardware. But software, you can get it and try and see whether it works at your site. And then later, if you want to do something, we can also then continue for that. So I will be talking this about an hour or like that. And during that talk, also I'll be doing some demo, actually the live demo. So processing the signal. I'll show you how it works and how simple it is. The theoretical part is quite complex inside, so I'm not going to do all these theories and how it works, how it is computed, all these mathematics and all. So this is not the purpose of this training. So we'll just show you what are the things available and how easily and how cheaply at very low cost you can do this. Okay, that's the main purpose. And after that, so please do some data processing at your site, and also we can have this Q&A or discussion during this time interval. And also during this time, we will show you a little bit about the Android data logging system, Rtk Droid or other Madroid or other software that we have. So Abhinav will help this to do a little bit of 10-15 minutes of this demo or showing you the app, how it is working to collect the data. So it will be just an online demo, okay? No this theoretical presentations and so on. Then we'll have a break, and during this break, so we'd like to have your evaluation, enter to the system that Patrick has sent you already, I think. So please do that. And then please let us know who would like to do some presentation work. So we have 3 minutes each. So I think this is 1.5 hours. So maybe we may not have this long time. It depends on how many you want to do, or we want to do more on the RTK data processing. So we can adjust time today. Maybe we can extend this to somewhere here, or you can have a presentation and see how many of you, if there are only 10%, so maybe we need just half an hour, and then we can extend another 1 hour for this type of data processing, or to have just a very free discussions on the RTK or data processing that we had so far. And then at the end, we would like to finish this work, but this is just a tentative time plan. So basically today we'll be spending more time on the data processing and more on the free discussions that we have, okay, and also the demo we do. Okay, so this is my slide, that file. I think you already have it, or you can access from ICG website. So now just a question to you. So I suppose that many of you already have this price information about the receiver. If you want to buy a receiver, so how much it costs? Maybe some of you say maybe at least $500 like that, or maybe $100. So minimum will be 100, maybe, and more. And some of the course receiver that is used for course, they are a bit expensive, or quite expensive, maybe $10,000 or more. And there are reasons why it's so expensive. Okay, but also like the receiver you have in your smartphone is less than $10. Maybe the chip is just the chip itself, maybe just $1 or $2 or $3. I don't think it's more than $3 in a smartphone. Yeah, otherwise, it's not possible to do the market. And also, it's millions or billions of pieces, so it's a volume. Okay, but of course, you don't have that much of volume. That's one of the reasons why it's so expensive. And but what accuracy you can get from a GNSS receiver? Okay, so theoretically, we know that if we have 4 satellites, we can compute the position data. And these satellites are GPS, Galileo, GLONASS, Beidou, QG, or Navig. Okay, so mathematically, you should get the same accuracy, whether you have this in the mobile phone, whether you have this in the course, or whether you have this in the tripod or whatever on the car or what. But there are so many other factors. Okay, the way the signals are being observed, the way the signals are being processed inside the receiver, and the type of the antenna, and the noise factors, and so on. So it makes the overall performance quite different. Okay, and finally, actually it depends on you how you want to use and for what. So what type of applications are you going to use? Are you going to use for surveying or mapping and GIS applications, or is it the geodesy? Are you going to use it for aerial photographs or drones mapping? Okay, aerial mapping, aerial survey, or maybe you are going to use for transportation. Maybe you are going to use for some utilities management. There are so many applications. So whenever or wherever you need position data or time data. So actually we also use time GPS for time data, not only for position. So it's position and time, like in communications or finance and other utilities, they also need the time. So wherever you need the position data or time data, you will be using the GPS. Okay, so you need to define for what you want to use and what are your accuracy requirements, because normally when we ask people, so what accuracy do you want? They said they want to have the maximum possible. They say centimeter. Some people come and say, oh, they want a millimeter, but do you really need the centimeter accuracy? Okay, so this is very important, because when you go to the centimeter, the way you have to do the survey, the way you do all this data processing, they are completely different. Okay, you just can't put the antenna on a car and run it, and then you try to get the centimeter. That's impossible. Okay, it's completely different way. It's quite complex, and there are so many things you have to prepare. It's not possible just a simple observation. So you have to decide what you want to do and what accuracy you are looking for. If your requirement is very, very severe, like you really need within the 10 centimeter, so you have to make sure whether you really need it. For example, in a precise agriculture or precision farming, they do need the accuracy within plus minus 5 centimeter. Okay, so that's better. They need accuracy better than 10 centimeter or even better than 5 centimeter. It's a very precise requirement. So then the system has to be developed for such applications, especially. Okay, it's possible, but you need a very customized system for that. And for transportation, the accuracy for autonomous and all, the requirement, it says the 30 centimeter to know the lane changing and all these things, okay, for automated driving. So how to provide the 30 centimeter accuracy? That means plus or minus 15 centimeter. Okay, when we say 30, means you must have a accuracy requirement of plus minus 15 centimeter. So that's very, very strict requirement. But when you go below 10 centimeter or 10 to 30 centimeter is again a very big difference. Okay, after between 10 to 30 centimeter or below 10 centimeter or below 1 meter or between 70 like 50 to 100 centimeter. So all these small figures now they become very, very important to get the accuracy, and there are different ways of data processing technique for that, and you have to then decide which signal, which frequencies, whether L1 only is enough or not, whether you need L1, L2, or whether you need L1, L5, what type of antenna, whether it is a static, whether it is a moving, dynamic, so the data logging method, so whether you do a point survey, point to point, okay, you are not doing the survey in a continuous way. Okay. So whether you do the point-to-point survey static mode, so this means you put tripod on the point and you have enough time to observe for half an hour or 1 hour or even multiple hours. Okay, so this is a completely different way of observing than the dynamic mode, because when you are moving in a car at the 50 kilometer or 100 kilometer per hour, so at certain distance, you have only one epoch of observation. So if your output is 1 hertz, you have one measurement in 1 second. So you are measuring 1 second interval. So in 1 second, the car has already traveled some distance. So every certain distance, you have only one observation, and whether that one epoch, the single observation is good enough or not. Okay, because in a static, we have an opportunity to calculate the mean and all, because we have multiple observations. So we have many number of samples here at the same point. But in dynamic, we don't have it. We have only 1 point, so you can't do any averaging anything. Okay, so you have to trust on that single epoch observation. So how to get the single epoch observation with centimeter accuracy is very, very challenging. And also whether you need this in real time or post processing. So most of the applications they can only use in real time, like car navigation. So you need the information in real time. Okay, whether your real time system can give you centimeter accuracy or not. Of course, in post processing, you have capacity to do centimeter accuracy, but how about the real time? So that's another factor. So all these requirements have to be defined, and based on that, then you can choose your system and you can choose your hardware or software and all. So then this price factor comes forward. Then sometimes maybe, okay, you need to pay maybe more than $10,000, but in many cases, okay, it's within $1,000. Okay. So these are the important factors that we need to decide before you choose your receiver. But from the education or training viewpoint, so we are going to stick around this level, maybe around here, to try different types of receivers. So I will talk about some of the low-cost systems, and before that, so I want to make a definition of what we mean by low cost, or we don't say high cost, but we said high-end survey grade receivers. So basically the difference is between the signals. For example, these are all the signals that I took from I think this is from the Galileo Navipedia website. So you can see it's too crowded now. So many signals from in L1 band, L1, E1, B1, okay, GPS, Galileo, Beidou, so many different frequencies. So GLONASS is here. And so you see lots of different types of signals. And also, even if you have only one L1 frequency, you still have so many signals in L1, L1CA. This is L1CA, L1C we have here, L1CA, L1C, and other Bok modulated signals. Okay, so many different types of signals are here. It's too crowded. And then we have L6, B6, E6, and B3. So E6 is also going to provide PPP service. They call HAS. Okay, so where is here? Galileo. So E6 and L2 receiver. So far, L1 and L2 is quite popular receiver because these signals were available from the beginning when GPS was started, but recently new signals have been added. That's in L6, L5, and all these E5, B2, L3 are all new signals. Okay, E1, B1, E6. So this L6 is all new. And at the moment, also L6 receivers are not easily available, so very limited. Only probably the high-end receivers are available, not so price friendly. It's a bit expensive and so on. But if you look at this chart, so also I explained a little bit yesterday that this L1, the L1 here and L5 is too crowded with the signals. So what we can expect in future is that we will probably have a very low cost systems with L1 and L5. Okay, so this is my expectation a few years ago, and now it's coming up like that. We don't see much L1 and L2 receiver in the low cost or in the mobile phone or this for the mass market chips. So they, I think, probably designed for L1 and L5, because if they design for L1 and L5, this will accommodate most of the service providers signals like a GPS, this GLONASS CDMA, and Galileo, Compass, Beidou, QGIS, and also the Indian system, because they broadcast only in L5. So L5 getting the most crowded now. And so these two signals will be quite common in future, or maybe for the low cost. But if you go for the high end, so they have all these options, L1, L2, L5, and you can choose whatever frequencies you need. Now, if you say, I want everything, I think the price goes quite high. So you have to choose whether you want to stick to L1, L2 or L1, L5. Okay, if you want everything, then I think the price is more. But the receiver by hardware design itself, I think their front end and all, they are generally designed to have all these capabilities, the high end. So they control the price by the license you buy for that, because to adding one more frequency when they already have two, the cost for the manufacturers is not much. But what it affects them is all the signal processing memories and CPUs and so on. Okay, processing capability, the memory, they need more memories and so on. And also then you have to add the antenna that is capable to log all these signals. So the front end itself, the receiving hardware is, I think the cost is not much, whether you have only 2 frequencies or 3 frequencies. And also whether you want to have everything or just a few systems, like if you want to buy only GPS and GLONASS, so that's one story. But if you want to have a GPS and like a Beidou, QG, that's another story. So if you say if you want to have everything every system, all the systems and all the signals. So maybe the price is going up. And when you buy this type of high-end receiver, so normally they have by default maybe GPS and some other signal, and they will ask you what type of signals you want to receive. And for every signal, probably they will charge maybe $1,000 or $2,000. And if there are 10 signals you choose, so you already have more than $10,000 additional on top of the base price. So if the base price is 10,000, so you'll add up another maybe $5,000 to $10,000. Okay. So that's the reason the cost goes up, maybe from 3 to 10,000 or 30,000 and so on, and all these things. Okay, but nevertheless, the low cost is also now we have L1, and they already have all the satellite systems like U-Blocks and many other products. So they can receive GPS, Galileo, GLONASS, Beidou, QZ, even S-Bus, and so on. But Navic is not yet so common. It's now coming up slowly. We have already, you saw in the Navic presentation on day 1. So there were some chips that's all capable to do Navic, but that means L5. So, but when they put L5, so this is in this L5 region, one more frequency band. But I don't know whether this low-cost Navic-capable receiver can also receive all the satellite systems, GPS, GLONASS, Galileo, Beidou, and all. It's a lot of channel they require. Okay, it's not that easy. So the even low cost, we have multi-system now. Okay, like U-Blocks, MAT or F9. And basically it's single frequency, but now also we have a multi-frequency L1, L5 or L1, L2. So we already have L1, L2 systems. Also L1, L5 is coming up like a Broadcom chipsets in some of the smartphones. So we already have L1, L5. U-Blocks is now L1, L2. Okay. And then the cost is about $200. It varies from if you want only L1, so it's about $60, $70 or less than $100, including antenna. But if you want the 2 frequency, the cost is still around $300, including the antenna. Okay. So our target, this is our target. So expecting less than within $100. It's not possible at the moment, but maybe in the next 1 or 2 years, it should be possible. So my definition or our definition here is when we say low cost receiver means it's a price. So we expect around $100 US, but at the moment it's not possible. It's a bit difficult, and accuracy is better, should be 100 centimeter, means 1 meter, better than 1 meter accuracy. Or it can give you maybe 30 centimeter or 50 centimeter, but anyway, we want better than 100 centimeter. This is okay, we can get it, okay. And also the weight is okay. So we can have this one and this one. Sometimes this is a little bit bigger with the antenna and other parts. So, but main problem is this price. Okay, but I expect this price will also go down in the next maybe 2 years, probably. So this is my definition of low cost. So everything is 100, okay, or less than 100. But the question is, when we have this type of low cost and very, very small size system, so can we still get the high accuracy? Okay, so maybe we may have to compromise here. Of course, we can get the low cost system, but how about accuracy? It may, if the accuracy is 5 meter or 10 meter, so it doesn't make any sense. Okay, so the point is that we want to have this high accuracy with the low cost system. So this is the thing that we are trying to do, how to achieve this one. But we are not the chip makers or the receiver manufacturers, so we have to rely on whatever is available. The only thing we can do is by using the software and the data processing technique. Okay, so being engineers in this field, so all the people who are doing developing the algorithm, data processing, RTK, PPP, so if they make a better error correction technique, probably it's possible to do that, to achieve. So the normal accuracy of GPS is 10 meter. Okay, this is not only GPS, but any system. So it's a few meters, maybe 5 meters or 10 meters like that. So nowadays, I think we had some figures in this ranging errors and all. It's a few meters, so it's not a centimeter. It's not possible to have a centimeter accuracy without doing any error correction technique. So since you have to do the error correction technique in the receiver, even if it is a very high-end receiver, so why not to have develop a good algorithm so that you can get the centimeter level accuracy. So that's the point. And I showed you this yesterday, and we saw the actual data processing. Probably you have seen yourself this. This is the data for 24 hours. The same data set from this receiver. I think in this case, this is I think the low cost receiver, not the high cost, high end. So if you put the data antenna for 24 hours, you get the data like this, and you see these chunks of the scatter points moving all the way around. Okay, you see this extension here and going like this. So this is because you see the scatters. If you look at this, so you will see some groups of points moving here and there. Okay, so if we look this, so any point we take, for example, if you are moving, so you have only one of these points, but this point may be anywhere within this graph. Okay, it may be here or it may be here. That means the accuracy of this is plus or minus, so 5 meters. So that's 10 meters of accuracy. So we can guarantee that by taking just one epoch, you are within 10 meters of or 5 meters of the radius. Okay, that we can guarantee that one. But if you ask me, okay, can you give me a 1 meter of accuracy? Then I can say yes, but the probability is just maybe 50%. Okay, CEP. So, but the 50% of measurement, you may be within the 3 meters, but the rest we don't know. You may be off by 20 meters, you may be off by 10 meters, so we can't guarantee. But if you want to guarantee in your system, or the application requires that guaranteed accuracy to do all these performance, then if you look at all these, so you just take any point, so they are probably within the plus or minus 5 meters, like that. So your guaranteed accuracy is 5 meters radius plus or minus 5 meters. So that's the total is a 10 meter. That means you can be anywhere within 10 meters. That's the guarantee. So this is what we are talking. So you have to remove some of these errors to do this one. So this is using the DGPS, differential GPS, using only the code phase correction. So this will remove some bias, and now you see the nicely center around the origin, and you have all this. Now if you take a mean of this, so this is a very, very small mean data, and you will also have a standard deviation here, so it's much better. But again, if you are moving, so you may be one of these points, so then again, the guarantee, the accuracy that we can guarantee is now 2 or 3 meters, okay? So this may be about the 3 meters. 1 to 3 meters of accuracy is possible with the DGPS. But when we process the same data, so this is the same data, the red points, blue points, and then we go to the RTK, and then we can get a few centimeters of accuracy. So then here in this case, then we can guarantee, okay, now I can guarantee you 2 centimeter or 5 centimeter of accuracy. Okay, even if you take one epoch, so you may be within these 5, this is 5 centimeter, 5 centimeter, and this is much, much smaller. So I think the accuracy we can guarantee within 5 centimeter to say that, okay, use this receiver, use this processing technique, your accuracy is within 5 centimeter. That we can guarantee then. But to do this, we need a lot of other resources, and the observation techniques are different. The receiver you need is different. So the price goes from here to here to here. Okay, so the receiver that can just do this maybe just $30 or $20, like a Garmin, some other very standard normal receivers available in the market. Maybe you can buy for $50 like that. And when you go to this one, which is capable, you can see the receiver capable of doing SBUS and DGPS. They may be a little bit expensive, maybe $100. in the market. And if you go here, that it will be maybe at least $300 to $1,000 at least. Okay, so it goes up because it needs a more processing capability. So more CPU, stronger CPU, and more memory. So all these adds up the price. And also you need the correction data service from somewhere. So yesterday I explained this a little bit. So I don't know whether everybody was there yesterday or not. Anyway, let me repeat this one. So the reason why we have this, okay, you see all the errors here is because of these factors. Okay, so we have the satellite orbit error, means the GPS is moving around the following the orbit that is defined in the system. But this goes around and around the GPS satellite in the orbit, but still it drifts a little bit due to various gravitational or other forces in the space. So it has a very small drift, and that drift has to be corrected. So the satellite system providers, they have this control point located around the world. Okay. Like for GPS, I think they have 7 or 10 stations. Also, Galileo, they have a few multiple stations. I don't know how many in total, but there are so many these monitoring stations or control stations. So it's constantly getting the signal from the satellite, and also they have some laser ranging instruments. So it's shooting the laser beams to the satellite and measuring the range, the distance, and see how much the drifts are there. So all these things are there calculated, and then the orbit parameters are updated every 2 hours or 4 hours or every 1 hour. And for new systems like a QGIS, so it's even I think that some parameters are updated every half an hour or even every 10 minutes. Okay, so it's very frequent update of these orbit error correction data. So if you can know the error, if you can compute the error or measure the error, so this can be provided to the user, or you can update in the satellite. But in the satellite, you can't update so frequently, okay, because the satellite has to be visible from your control station, because these satellites are moving all the time. It's not geostationary, so it will take some time. So this error, by somehow, if you can get, or if we can send this error to the receiver, you can remove this. Okay, so also for satellite clock is the same. The satellites have a very highly accurate atomic clocks, RubyGM or CGM or even hydrogen measure clocks, but still they have a very small drift, and that small drift is contributing to some error here. Okay, so this is about a few meters, 2 meters and 2 meters, but these two errors, they can be monitored and measured or corrected, calculated, and they can be removed, yeah, doing different types of techniques. So one of the techniques is the differential observation, and this one is the ionosphere and troposphere error, but it's a bit large, but it cannot be removed totally. It can be minimized by doing again the observations, measurements. Measurements means observations in the receiver using L1, L2, or doing some there are different types of models for this. So using these techniques, it can be reduced. So we have to remove or reduce the errors as much as possible, doing different types of techniques. And this one we cannot. These are the reflection from the surrounding objects, so we cannot remove it. Okay, this will remain. So you have to do in the open environment or multipart free for this very highly accurate position data. So the way we do the removal of the error, so this is again repeated on day 1. You saw something this in the Galileo presentation, and also yesterday Mr. Kubo's presentation, and so I'm showing it once again. So you need to put a station here, base station, or we also call course, which is continuously observing the satellites, coming all the signal. But this has to put at a non-point. Okay, you put at a non-point. So if you put at a non-point, so you can measure the error, okay, because you know what's the true value, and you are observing, and you get the error. So then you send this data, correction data, or actually we are sending the observation data from here to the rover. Okay, so in the rover, the software will calculate all the errors and do the correction here. Okay. So this is the differential correction technique. So that means in order to have this high accuracy to remove this type of errors, so you need to have a reference station. Okay, so this is additional infra. So we talk about the what is the distance. So many questions here, best length. So I'm saying that it shall be less than 40 kilometers or like that. So higher the distance, the larger the error, and it's not very effective for centimeter level of accuracy. Of course, you can do the data processing, but you don't get that high level of accuracy. And there are also techniques to do the long range best length RTK. So some algorithms are developed, but you won't get the same centimeter level of accuracy in that case. You can do it, but you can't get the accuracy. You can't. It's not possible. I don't say not possible, but it's quite difficult. And so this is the Madoka. So this is what we are going to see today. So this is a quite new actually. So many of you, I don't know whether you have heard this name or not. Madoka, I think it's a long abbreviation. I don't remember this. So this is basically the PPP, precise point positioning. So here in RTK or differential correction, DGPS or this kinematic. So we are sending the data from the base station to the rover. Okay, and this must be installed at a non-point. So if you want to cover the whole country, you have to have so many of these. So if one base station costs $10,000 at least, so I don't know, if you need 100 base station for your country, so you multiply 100 by 10,000 just for the system. And on top of that, you need annual maintenance and all this infrastructure. So how to send the data, how to store the data, how to process the data. So all these communication costs, everything will be added up, and that's a huge cost for that. So to avoid this, maybe we can send the correction data, this type of correction data, directly from the satellite to the receiver. Okay, so this is what it does. So the QGIS satellite, they have one additional frequency, L6. So this L6 signal now sending the correction data. So we call the correction data Madoka, and two types of signal actually, Madoka PPP, CSIS PPP. So the correction data of the orbit error, clock error is coming from the satellite to the receiver. Okay, so you don't need any base station then. But the problem is that then you need to have a receiver that can receive this signal. So this is now using L6. So in Galileo, it is a E6. So currently, if you want to buy Madoka capable L6 or E6, Galileo capable E6 receiver, so very few products are available and they are quite expensive. So I think, I don't know how much it costs, but maybe at least $5,000 or more, or even some receivers, they cost more than $10,000. So about 5-6 years ago, so this cost about $20,000 or $30,000 only for Madoka. But now the cost has gone down to maybe 5,000 around or 3,000. I don't know the exact commercial cost for the receiver. That is Madoka possible. But this is a very, very good function of this QGIS. So we thought that we cannot afford this $5,000 or $10,000 receiver. We can't afford even $1,000 in the university. So we proposed to have a very, very low cost receiver. And this is what we did now. Now we have a very low cost system, and we can do this Madoka easily. Okay, so you will be getting orbit error data and clock error correction data from the satellite directly, and the receiver, Madoka receiver, will receive this and do the PPP. But unfortunately, this low-cost Madoka receiver is not yet commercially available. I think it will be available very soon, maybe this year, because the company manufacturer is saying that it would be available last year, but due to various reasons, it was delayed. So maybe in this year, so it will be available. So we already have a software. So once it is available, so you can use our software and do the correction data. But another limit of this is that because this signal is broadcasted by QGSS, the Japanese satellite, and this satellite is not visible all over the world. It's visible in basically in Asia and Pacific regions. So Asia, Oceanic, so Japan and Asian countries and Australia, New Zealand, and some Pacific islands, and maybe a little bit the north of Asia, and okay, but not the global. So you can't see this in many parts of Europe. You can't see this in the USA. You can't see this in Africa. Okay. Also Brazil, I mean South America, you cannot see this. So America, North, South is not visible. Africa is not visible. Okay. And many countries in Europe is not visible. So, but it doesn't mean that it's not usable, Madoka. So in the countries where QGIS is not visible directly, so what we do is we provide this correction data from the internet. Okay. So as long as you have internet connectivity, you can get this correction signal or correction data through the internet. Internet means you have to access one of the Ntrip servers that we have, and then you can get this Madoka Ppp service. But this service is now provided by a company in Japan called GPass. So probably they may have some fee on that using the service. I don't know whether this will be free or there will be some charge on that. Okay. But the signal itself, which is coming from the satellite, is free. So if you can receive the signal, if you can develop your own program, you don't have to pay anything. Okay. So that's the thing about the Madoka, how it works and what has been done. Now let me show you some of the systems that we have. And basically we have two types of system, one for RTK and one for Madoka Ppp. So we call this is this is rather old slide in the very beginning. So we made this type of system based on the Raspberry Pi. So this is necessary to reduce the total cost of the system, not only the receiver, but also the computer. Because these low-cost receivers, they don't have a computer, they don't have a signal logging capacity or processing or interface. It's just a receiver, okay, like a uBlocks MAT. It's only a receiver, and to use that receiver, then you need a computer, and that computer costs $1,000. So as a system whole, it's not cheap. Because if you buy $1,000 receiver, that will probably have all the logging facilities. So how to reduce the total cost is by replacing the computer by this type of device like a Raspberry Pi. So this is cheap, $50–60 of device. So you have another $60. So that's why the cost is around $300. And then this Raspberry Pi can send the data to Bluetooth to your tablet or to the server or whatever. So you can do either real time or post processing. Okay, and depending on your application, so it can be Raspberry Pi, or if you just want to log the data for post processing, you can even use this $10 or $15 Raspberry Pi Zero. You just log the data here. Okay, it has a SD card, so you can log the data here. Or you can directly connect to the Android device and your receiver and log the data here. So this is the Rtk Droid. So we have this app already distributed. Some of you send the request, so I already send the password to you. So please test whether it works or not. But please make sure that this receiver has to be set for RTK capability to log the raw data. If you don't set this to log the raw data, it will not work. Okay. And please do the test outside of the building, because in the past, many people do the test antenna in the window. And when you put the antenna in the window, the signal is not good. The CN0 is low and it doesn't work. And we tune this app a little bit to have a good signal. So the threshold for the CN0 is a few dBs higher than the standard receiver. So you have to go out to do have a good Rtk Droid accuracy. Okay, so many people do inside because they say, oh, it's too hot to go outside. So if you say that, so this is not for you. Okay, And this is for Madoka for Droid. So also we have this. So this is the same thing. So you can use the same receiver. Same receiver means you need this one. You can use the L1. Okay, for RTK you can use L1 or L1 L2. But here you need the L1 L2 receiver for Madoka for Droid. So you can connect this to Droid and do the same thing. The PPP. This one is for RTK. This one is for PPP. I will skip this. Okay. And these are some screenshots of Rtk Droid and Droid. So today I have Abhinav who will show you later about the Rtk Droid. He is now doing some setup in the Kathmandu. He will show you how it works, and I will show you about not the Droid but also Madwin, using the online correction data. So for example, if somebody from Africa or South America, they want to do the Madoka PPP, so I will show how to do that, okay, by getting the correction data online. So these are the screenshots of the apps, how it works. And regarding the low-cost Madoka system, so we have a 3 version Madoka Pi. This is using the Raspberry Pi, so you don't need a computer because computer again adds a cost. So you just buy a Raspberry Pi, that's a $50–60 computer, and connect to Raspberry Pi. Okay, so this is one way of working. And it works with different types of L1, L2 receiver, U-Block, Septentrio, or any other receiver that can output in RTCM3. Okay? And the correction data, so you need a receiver that output in UBX, RTCM, or if you don't have a receiver, or if satellite is not visible, then you can access online. But this JAXA Online is not available now. We are providing from our university this online service at the moment. Or GPass company, they are also providing this online service. This is the Madwin. This is in the Windows version. Some of you already got it because I don't know whether they are attending this training now. So we distributed this a few months back in November, I think October or November. And this Madwin works in the Windows, but they expire every year in December. So we also produce new release. So some of you, if you are using, so probably that's already expired. So you can access again the new version. Please download the new one and then it works again. So we have updated the new one. So this is for Windows, this is for Raspberry Pi, and this is for Android. Okay? So you can use any platform. But this one, we had some issues depending on the Android device. It's a bit difficult because around the world, there are so many different types of Android devices with different versions of OS. It's very, very difficult to make it compatible with all the devices. So it may not work with your device, but the best is to try with the Windows or the Raspberry Pi. Okay. And this is how it works. You connect the antenna to the receiver, Raspberry Pi and all. But since this is a Madoka, so you need to have at least L1, L2, and L6 capable antenna. So when you buy L1, L2, and L6, so you will also have a L5 by default because the manufacturers, they are not making the antenna like L1, L2, L6. They are, if you ask for L6 and L1, L2, you will also get L5. So that means you need an antenna that is capable of all the frequencies. But at the moment, this Madoka is using only GPS, GLONASS, and QGSS. So you need the antenna that is capable to receive GPS and GLONASS, because GPS and QGSS is the same in terms of signal and frequency. GLONASS is a bit different. So you need to buy GPS, GLONASS, and QGSS compatible antenna with L1, L2, and L6 frequencies compatibility. So that's the requirement for antenna. And the receiver is L1, L2, and L6. Okay. So this one you have in the market. So any L1, L2 receiver that can output the raw data is okay. But Madoka at the moment is not available. I don't know whether it's already in the market or not, but at least last year until November or December, it was not. So this we have some samples to provide, but this is very, very limited. And if you don't have this, so you can get like L1, L2, you have only this receiver, then you can get the correction data from our server, okay, or from GPass or JAXA, like that. So you can get, but you need the internet access then all the time. So to have internet access, probably there may be some cost at your side. So this is the receiver that we have. You see it's very, very small, about 6 centimeter, 5.5 centimeter. So this is, let's say 6 by 6 centimeter, about 1 centimeter thick. So it's a very small, very compact receiver. It's smaller than a mouse. So this mouse has nothing to do with the receiver. So I'm putting here just to show you the compatible size between these two. Okay, you see it's very small. And here's you connect the antenna. So this is the antenna that we have at the moment. So you can connect any other L1, L2, L6 compatible antenna here. Okay. So inside we have a L1, L2, the F9P receiver. Okay, and this is the Madoka decoder we have. So actually inside this box there are 2 receivers. So 2 receivers, 1 antenna and 1 output. Okay, it's made very compact. So antenna and the splitter, so this will split the signal to both the receiver and then combine output to 1 USB port, and you get 2 output ports here. And you have to set up these ports like this, and then you can get the signal. Okay. And you can check these signals in uBlocks as well. So if you look at this F9, this is the F9 receiver. So the raw data, pseudo range, carrier phase. So you have to output these pseudo range and carrier phase data to do the Madoka or RTK. So this is same for RTK or Madoka. You need the raw data, but also it outputs other like a Doppler or SNR and so on. Okay, you see so many satellites here: GPS, Beidou, QZ. R is GLONASS, and E is Galileo Europe. And these are the navigation data coming up from the F9P receiver for all visible satellites. So we need the raw data, pseudo range, carrier phase, the observation data, what we call, and these are the navigation data. So coming up from the signals that are visible. And then Madoka satellite system and signal settings. So F9P receiver, and this is the Madoka decoder in the uBlocks. So you can also see how it looks like. So for the F9P, so you can choose which satellites to enable or disable. Okay, configure enable. So here you can change. Okay, so I'm just putting all on to log all the data, because I can log the raw data also while doing Madoka, so I can also do the post-processing kinematic or RTK later. Okay, so I can log all. And here is the Madoka setting, so it's only QGIS. Okay. Satellite signals and systems. So this I'll show you later in the details. And these are the Madoka correction data coming from the satellite. So it comes in the binary format. So if you look at it in uBlocks, so this is the stream coming up in the Madoka, because the Madoka data stream is it broadcasted at very high rate, about it's 2 kilobits per sec. That means every second you get 1 frame, and that frame has 2000 bits. Okay. Other signals like a GPS L1CA, that's a 50 bits per sec. It's very slow. But Madoka, this navigation data is a 2000 bits per sec. Okay. So 40 times faster than GPS data. So that means you get a lot of these bits here in 1 second. Okay. And this is the actual size. Okay, this is a Raspberry Pi with the touch screen, the Raspberry Pi with touch screen, and we have the receiver here, and here's the antenna and the USB device to log the data, and this is how it looks like. The satellite, visible satellites already tracked and did the PPP position. So overall picture is here. So antenna, pole, Raspberry Pi, and GNSS. So it's something like this. So this is our campus. So This was last year after we just finished the development, not the last year, I think 2019 December, so already more than 1 year. Okay, so this is very compact. You see the size is very, very small. And these are all the settings that you get in the software in the Madwin for Windows or Raspberry Pi. It's same interface. So if you have external GPS receivers, so you choose RX and DX. This is for GPS. This is for, I mean, the GNSS. This is for Madoka. And if you have only the external GNSS receiver but no Madoka decoder, then you get the online Madoka correction data by selecting here. Okay, so this is how it works. If you want to do everything online, like you are at home and due to COVID and your receiver is in the field or in the office, and you can access your receiver online. So select online, then you can do the online processing. Okay. And this is how it looks like. So one thing in the Madoka is that the moment you connect, your error is not a centimeter. Okay, it will be maybe 10 meters of error. And as time passes by, it takes about 20 minutes for this augmentation AR convergence. Sorry, not AR, for the convergence of this PPP. So it takes about 20 minutes, at least 10 minutes, then maybe up to 20 minutes to give you 10 to 20 centimeter of accuracy. So you have to wait, okay, in a static mode. So this is one requirement, and this is minus. I think this data is, I think in Bali in Indonesia. Okay, so I was just testing in the different countries. So this was data log in the Bali. So it was working. Okay. So as the time passed by, this is in Tokyo. So you see in the beginning about 1 or 2 meters of accuracy, and as the time passed by, you get a very high accuracy of maybe a few centimeters, even 6 or like that. Then it says you PPP solution here. So this coordinates, we can take this as an absolute coordinate, okay, true value. And this is the interface for Madroid in the Android. So you connect the Madoka with the Android device, and we can do the similar thing, UBX, Septento receiver, uBlocks receiver, or other receiver. Okay. So the working is same, but the interface is a little bit different. And in this case, during this development, so we have to access the correction data through Ntrip online, not from the satellite directly. So the interface was like this, but now I think we have already modified this, so we can do direct from the satellite. So this is how the data looks like. So the sky plot with the satellites and the signal level, and some output data. And here you see the lat long coordinate, and also you see the coordinate in the UTM. So when you see the coordinate in UTM, so this is in meters, planar coordinate system. This is the spherical coordinate. So here it's a little bit difficult to find out how much error is there. If you look at this planar coordinate system, so when you get a centimeter level of accuracy, probably this 0.7 is almost, it should be fixed, should not change with respect to time. Maybe the second digit will be changing from time to time. That means, you know, okay, now you have a centimeter level of stable accuracy. Okay, so these figures will not change at all, and that's very interesting to see how accurate is this observation. Okay. And these are just some experiments. So we observe here for 10-15 minutes, and then we walk. We walk means we hold this antenna on a tripod, and then just walk. I think we put every point on this grid, and then we walk, okay, straight. And when we plot overlay with this Google map, it's very nicely overlaid. Okay, in Japan, this type of urban area Google map is also of very high accuracy. I think they have accuracy of about 20 to 30 centimeters from aerial photo. Okay, so also we have this PPP AR capability. So we are doing this test, but this is not fully yet done, but this is our next to have a more better accuracy from PPP or smaller convergence time. So this will be available in future, but not at the moment. Okay, so that's all. I think these are the same thing, but coming from the Raspberry Pi. And you see that this is the convergence time. So when you just connect, okay, so the error is very large. Oh, sorry. And after 10 minutes or like that, so maybe here is about 20 minutes, then it becomes more smooth and very stable output. So this time you have to wait. Okay, so here is quite large. You see this fluctuation, and then it becomes stable as the time passes by. And this one, I don't know how long I observe for. So this is the measurement by Madoka. These are the reference value, true value. Then we have this level of error in our campus. Okay. And so we did this similar thing in other countries. And the same thing. This one is plotted here. Okay. This one is in the beginning here. And when it's stable, it's about the 10 centimeter. This is a 10 centimeter radius circle. Okay, so it's like this. And we did a similar thing in Indonesia and also some other countries, I think in Thailand and also Egypt. So we tested in Egypt because from Egypt we can't see QGIS, and also Egypt it was okay in Cairo. Okay, so that's all from my side at the moment, and I would like to show you some demo. So it's almost more than 1 hour. It took a little bit more than I expected. So, so let me take a few questions at this point, and then I will prepare for demo here, and also Abhinav will make a demo. Just show the Rtk Droid. So let me show you the Madroid first, but before doing that, let me take some questions if you have. Okay, where are the questions? Can Shafa help me to find out the first question, or where is it?
Yes, just give me a second. There were.
Okay, I can see. Okay, here 347. The base station correct location. We can use PPP to get that instead of using land surveyors. Yes, yeah, that's what I think. Yes, so I don't know what you mean by using land surveyors. Do you mean the traditional surveying methods? Like yesterday we also discussed about the optical survey using all these conventional surveys. If you can do that type of survey, for example, you have the horizontal and the vertical point that we needed, of course. So that's every country is there. You have a reference point, so we do need that type of point. Okay, because when we convert from the GPS coordinate to the local, so you need some reference point. For that we need it. But to do like whether we should do RTK or whether we should do PPP, as I explained or we discussed yesterday, so we found that PPP is better than RTK to have an absolute coordinate value, because to generate the PPP correction data, so many background informations are used related with the orbit error correction data, clock error correction data, and these are computed by using the stations around the world. It's not just a few stations in Japan. Okay, so we use so many stations around the world to see many different types of compute many different types of error correction data using the art movement and all. So there are so many factors that are being used to generate these correction data. That's the reason PPP gives you better data. I mean, near to the absolute coordinate system, absolute position data. Yeah. How error in satellite orbit is computed in DGPS by the base station. It only knows its coordinates, right? Yes. So that's a differential correction. So you have, like, when you observe the same point from two different points, if you observe the same satellite from two different areas, and if you know one of the, the true point of your base station, then you know how much error in the base station, because you can easily calculate that error. But the problem is you have to know your base station coordinate very, very accurately. So if there's error, then you have error in your rover as well. But in DGPS, we use the coord phase only. So the coord phase is not that accurate as a carrier phase. So you can't have a very high accuracy in the coord phase correction data. So this some of the satellite orbit error and clock error are removed by this differential correction technique. But I don't think you can remove all the satellite orbit related errors or other Earth related errors. What software used to cast correction data from Raspberry Pi to what software used to cast correction data from Raspberry Pi to Internet Entry? We can use Rtk Leaf. Yeah, there are so many functions there in Rtk Leaf. Please share to access to Madroid. Yes, you can. Please, I send you the link to send the request. So you have to fill up the request form to us. And for Madoka, so we need to have it's a freely distribute, but we need to have some agreement with you. You means not individual, but with your organization or institute. Okay, because I don't think you will be having this type of all the logistics. I mean the multi-frequency antenna and all the receivers. So okay. Then use which RTK leaf version is used for RTK Droid? So I think Avinav has an answer. It was in B33. Okay, so Rtk Droid is now version B beta 3.3. Okay, so 3.4 will be updated later. Which L6 coder was the one in the photo? This L6 decoder is from uBlocks, but they have not, I think, commercially released this product. So I don't know. We have to wait. So we got some samples. Okay, so you have to wait some time to get this commercially available. Okay, and the next question, F9P is capable of driving L1, L2, and Madoka correction is being transmitted on L6. So how the correction is being applied? So that's why we had the two receiver inside. Okay, one is from F9P, L1, L2. And then we have another receiver that what we call Madoka decoder for L6. So we have two receivers inside that box. Does the test Madoka receiver system require constant access to a correction server? Yes, of course, it is required. There are two receivers inside the test receiver box. Yeah, okay, this is reply from Abhinav. One of it, okay. So antenna, yep. Okay, thank you. And what's another? Why Google Map doesn't appear on RTK plot? So I think you have to have a license for Google Map. I think they have because now Google Map is stopped providing it. Freely. I don't know how RTK plot. I think there. Please check the RTK Leave homepage. I think there's some document there. Okay, how to do this. have used some of these for research studies. Ionospheric. Not for ionospheric. We are basically on the position data. So we are doing for our positioning applications, not for ionospheric. So, but for ionospheric, I don't think we need to see how we can do that. But ionospheric and all these is a little bit different issue and different topic. So I myself don't have a plan to do for ionospheric studies, but if you are interested, so we can see how it can be done. But we have a very special receiver for ionospheric, all these space weather related, very specially designed receivers now. So I plan to use those ones, not this one. I don't think I can do much on this. We don't have much control on this in terms of the signal acquisition and all tracking. Can Rtk Droid use the? No, we cannot do this from the internal Android devices at the moment. We cannot use Rtk Droid for internal Android receivers. We can at the moment. How to install Rtk Droid? How to install? Yeah, just download and APK, just the APK install. I have Alistar receiver that could get L1, L6. Could we process Madoka with it? I don't know. I don't have Alistar. So please ask Alistar company. I think they should know better because we really don't know how this Alistar receiver works inside and what it is tracking. So this type of information shall be provided by the manufacturer. So sorry, I don't have information on that. Okay, so let me show you the GUI, I mean the software, now how it is working. Let me set up. So I will stop this one and set up my trip. Mount point, Gus. So I'm setting my trip, so give me a few minutes. Yeah. Okay, now how can I share this? Okay. Can you see this small window? Madoka demo. Okay, now I have set my online. I'm accessing both online, and then I need to set up a start button, and now this is connected, and I should get my receivers, I mean the satellites, visible here after a few seconds, if everything is okay. Now you see, so let me record this. So you see very high error, okay, 5 meters like that. I'm not sure whether these small texts are clear at your side. Is it okay? Is it readable, the text?
Yes.
Okay. Okay. So you see the errors is still very large because the Madoka, now I'm getting the correction data. Actually, this correction data is coming directly from the satellite. I'm just accessing my receiver online because this is in the office and today I'm not in the office. Okay. So this is what I can do online, or I can, if I connect the receiver directly to my computer or Raspberry Pi, I select RxDX and set the COM ports. But now I'm accessing online with the Ntrip. So I'm not showing the setups because it has all the passwords visible. Unfortunately, the passwords are, we cannot hide it currently. Not so good for the Ntrips, all our servers. So this is how we access. Okay, so you see the coordinates, now it's changing. Okay, so the accuracy is still maybe this, maybe around 3 meters or 2 meters like that, like a DGPS level. But once it goes down to maybe 0.0 something, then it's very stable. Okay, so we have to wait another 10 or 15 minutes to go to very high accuracy. But I'm logging this data today now. So I will run it for another 15 or 20 minutes, and later, maybe after the break, I will show you how this data looks like. Okay, but this is a very simple. Okay, so if you have this software and the hardware, so just go to RxDX and connect your receiver with the COM port and press the start button. That's all. And if you wait for a few times, you get the high accuracy, and then you can log the data with go to the record, and okay, you can log to wherever you want. So this is now recording. The solution means the PPP output data, and this raw means the raw data from your receiver. So if you want to do post-processing kinematic, RTK or kinematic, you can still do RTK solution here. You use this file, this is the raw data, so you use the RTK leaf and do the post-processing. Okay, and these are the correction data coming from the satellite directly in the receiver that you have. Okay, so we are logging all the raw data in case if you want to do the post-processing. Normally you don't need these two files, but we just logging now for the post-processing capabilities as well. Okay. So this is our solution output. So we don't have you don't have to set like in RTK leaf. So what's the azimuth angle? I mean the all these mask angle and all. So we put I think 10 or 15 degrees by default and just process with all the default parameters. So we don't have any settings here. Yeah. So we made it very, very simple because our application, so we intend to use this type of application like in the machines, like a tractor. So if you want to do the precise farming, so you put the device on the tractor and the driver or the user just need to press a power button. That's all. Because the user, the end user should not be, or he or she won't be a GPS expert. So he doesn't know what is mask angle, which satellite, and what to do, all these things, carrier or code or okay. So the only thing is that if you press a button, it should give you the highest possible accuracy. So that's the design criteria of this interface. Okay. So everything is tuned inside the algorithm to give you the best possible data. So if this is bad, then it's bad. You can't get better than this then. Yeah. So this is how it works. So to considering the field, actual real environment, actual working deployment scenario. Okay, you just connect antenna receiver and to Raspberry Pi or another device, Android, and press a button, then it should work. Yeah. No such complex settings and all. You don't have to understand what's that or this. But for researchers, it may not be good because you don't have any control there. So in that case, then you have to use RTK leaf, because in RTK leaf, then you have so many parameters. You can play with all these parameters and see what is better for you, okay, in terms of your application, whether you are doing for very high accuracy application, whether you are going to do for static or dynamic and so on. Okay. Okay, this is all about Madoka. So I'm just showing you this MatWin for Windows, but also this is same for Raspberry Pi. and but it's a little bit different, the interface for Android. And so I will request Avinav to show the screen for Rtk Droid, and if possible, please show the screen for Madroid as well. So please show the screen for Rtk Droid first.
Rtk Droid. Okay.
Yeah. Are you ready? The settings?
Yes.
Okay, because now I'm in Japan and he's in Kathmandu in Nepal. So, okay, you can see his window. So this is how it looks like the Rtk Droid screen. Okay. So can you explain some of this?
Okay, so this is a very simple app. So you just select the connection, if you want USB or Bluetooth. So right now I'm connecting a L1 receiver, the M8T, low cost receiver, and it comes up here. And so this is uVlog, so you select format UBX. And then these are the only RTK-lib settings that you can change here. The rover mode, you can select either kinematic or static, and the elevation mask and ambiguity resolution. Right now I'll put continuous. And then the important setting, the encrypt settings, you can put in here your address, port, mount point, username, and password. And then you just press start and it asks if you want to record. Right now I'll say no. And then you will get your RTK solution here in some time. About 1 or 2 minutes. Oh, it's already here. So float RTK fix note. Oh. So this is a very easy to use app for RTK. So no need to change all the settings like in RTK lib.
Avinav, please scroll the window slowly because
Okay.
the refresh time
Okay.
at the participant's computer, maybe it takes more because of internet. So in the Rtk Droid, so have you explained about this entry? Yeah. Okay. Yeah. Getting the base station data. So in Rtk, we need to have a base station correction data coming from somewhere. Okay, so you need to have a nearest base station address, trip address. Okay. So this is now this is okay. This is so you see the lat long height and okay. So this is in the Kathmandu, Nepal. So how is the accuracy at this moment?
Yeah, so right now we're getting an RTK float.
This is float solution. Okay, it will take time. Okay, so unless you have a fixed solution, so we can't rely on this accuracy level. But the Rtk Droid, so have we changed whether we can select continuous or instantaneous? Is it possible to set up?
It here in the
it is possible. Setting. Okay. Okay. So, continuous. So in the ambiguity resolution, so you can select continuous, instantaneous, fix and hold, something like that. Yeah. And also we have elevation mask control, 15 degree, 10 degree. I think you can go very high as well. Yes. And now we see 20 satellites out of 20, 18 are used. By the way, so are you also using GLONASS here?
Yes, GLONASS here.
Oh.
GLONASS is on.
Okay. So I think it's better to put the GLONASS off. So this is the rover is a single frequency or dual?
Single frequency, M8T.
Okay. If it is single, so please, we have to put GLONASS off because the problem with GLONASS in this type of receiver is because GLONASS has FDMA modulation technique. So we didn't explain this modulation and all in this training in detail. So when you have a FDMA, So that means the receiver has, if there are different analog, I mean, every frequency, every channel is, every satellite is a different frequency. So in the receiver, you have a more analog components for every satellite. Okay. So these analog components will have a different level of frequency errors. So if you are combining or mixing two different makers receiver between the base and the rover, so this frequency bias or this frequency error will not be compensated, and that's what Professor Kubo explained. It's very difficult to have this ambiguity resolution using the GLONASS. So either your receiver must have a capability to solve this type of frequency bias, or we call also the interchannel bias, okay, in the GLONASS, or you should use the same base and the rover from the same maker. And even if you use the same, as the time passes by, the analog component, they keep on changing due to temperature and the age. So you need to constantly tune or do the settings for those type of things. So using this type of very cheap single frequency receiver, I think it's a little bit difficult to have a good fix in RTK when you also enable GLONASS. And also the GLONASS in the Asian region is, I think the performance is not as good as in the Europe or Russian because of this ephemeris update rate. Okay. So for RTK Droid, I recommend not to enable GLONASS for Asian region, but in this app, we cannot select that, I think. Can we select the satellites?
No, we have to use the uBlox uCenter.
Okay. Okay. So before you connect the uBlox receiver, so please disable GLONASS and then enable only GPS, Galileo, QZ, and Beidou. So that will give you a better result. That's our experience using this single frequency receiver. Okay. So, and this is just a replacement for your computer. So you can use a Android device instead of the computer. So is it still float?
Yes, still float. I think we cannot get a fix it because I'm using a very long antenna cable.
Okay, that may be another problem. Okay,
yeah.
Okay, yeah. But the signal quality is, I think it's quite good. The signal CN0, it's not so bad. Okay. Anyway, so please take a screen capture of this for the reference of your different screens. And can you now, after taking the screen capture, can you show us the Madroid as well?
Madroid, okay.
Just the screen is okay. Okay.
This is the Madroid app.
Yeah. Please explain a little bit on that.
So it has a similar interface. So you select USB or Bluetooth here, and then the device comes here. But Madroid needs the F9 receiver. It won't work with the MET, so it won't come here right now. And now we have the correction format, same as before, correction format, and then the correction source. You can select either online or the DX, the receiver. So if you select online, you get the encrypt settings here. And if you select receiver, no need to put in encrypt settings. And then the rover mode, you either select single, PPP, kinematic, or static. The static, then the elevation mask. And then you have to type in the antenna model for the PPP. You need a calibrated antenna, and then the antenna height setting is here, and then you press start rover. So after that, you get all the position solution here, and you can start or stop recording from this screen. So you set up first and then start recording.
Okay, so now Madroid, we can also use a receiver for Madoka. Okay,
Yes, latest version can use the receiver.
Okay, so we can use either online correction data or the Madoka receiver directly. Okay. Okay, so now he has not connected F9 receiver, dual frequency receiver. For Madoka, we need a F9 dual frequency receiver. Single frequency doesn't work. And internally, so if you have an antenna model, so you have to give this antenna model means you should have an antenna PCV database in this directory. I will show you later what files you should have it, because the PPP processing is a bit different. You need a PCB, phase center variation of the antenna of the receiver as well as the satellite. So you have to download some of these files from the other sources. And also we need the DCP, DCB, so code bias data, differential code bias data, and 2 or 3 other files. Okay, so I'll show you later. So this is all about the Rtk Droid and Mud Droid. And also Abhinav has developed his own some app to collect the GNSS data or for GIS data. So it's called what you call SW Maps.
SW Maps, yes.
Yeah, can you just show the SW Map screen so they can download later?
This is the SW Maps.
Can you show the GPS interface for SW Maps?
Okay, wait, let me start the Rtk Droid first. So
okay.
This app can work with Rtk Droid and you'll be used to record all your GIS data. So, and once.
So this SW map is very useful tool to collect the data in the field. So you can use Rtk data, Rtk Droid together with Rtk Droid, or you can use with internal GPS receiver. You can use with the external GPS receiver, any type of receiver. Okay, this is just data collection and GIS. Actually, the data collection for GIS. So you can develop. Make a layers, point layer, line layer, polygon, and so on to collect the data for the roads or points and so on. So can you show the interface for GPS?
Okay, so you can connect GPS receiver from here. USB.
Please do it a little bit slowly. It's very fast.
Okay, so the interface connection is all in here. So you can either pick Bluetooth or USB. So
okay.
Right now I'll go with USB and then select uBlocks. Let me stop Rtk Droid for now. And select the uBlocks and select the baud rate. So instrument model, I'm going to select uBlocks.
No. Okay. Again, this is very fast. Okay. So in the uBlocks, so we can also see others. Okay, you can also connect other receivers here.
So these instruments are
okay. Wait. So wait. You're going very fast. It's very fast. So we have a uBlocks. This is a standard uBlocks, okay, without RTK. When you say uBlocks, so you can have a uBlocks. You can have a uBlocks RTK. This is probably F9. Or yes. other receivers. Can you other receivers?
Septentrion.
Or if your receiver is not listed, you go to the generic NMEA. Okay, then you can get the NMEA data output to this app. Okay, so can you go to uBlocks? Okay, please show the skyplot or.
Okay, so it is connected now.
uBlocks is connected. Okay, can you show skyplot
on the map?
So this is where you are now in real time.
Yeah, and the skyplot is here.
Okay, please wait. So now here we see the time, lat long, and the height, and this is a single. Okay, we don't do any DGPS or RTK. This is a single point positioning or a standard positioning. We see 23 satellites out of 23, 19 are used, and here are the PDOP values. So you can guess the error you can expect with this. And these are the coordinates in lat long and the local UTM system. Okay, so this is the sky plot data and the CN0 and the visible satellite GPS and Galileo or QG. This is R is GLONASS and so on. Now, what
if you
else
want
we can
more information, you can see the Gnss Status page. It also shows your errors and accuracy, and your speed and coordinates. Yeah.
Mm-hmm. But okay, so I don't know whether this is really true or not. Latitude error is 71 millimeter.
This is what the receiver is reporting. So
okay.
That's the problem with the receiver.
Okay. So anyway, so we have a point. So this point is not fluctuating. Okay.
Okay.
So can you close this screen? Okay. So you see this red dot. Okay. This blue dot.
It's not blue.
Okay. It doesn't jump here and there because this antenna is on the rooftop of the building. So it's very clear sky. So this receiver is quite good. So actually, so it really doesn't jump here and there. Okay. Otherwise, if the accuracy is very bad, so it jumps here and there. So this seems to be very stable. So when you compute the mean from these type of observations, so your mean value is very good. So that probably that latitude longitude error is the mean of observation at certain interval. So that's why it's very small. But it does have the bias. Okay, so it's deviated from the true value, but the precision itself is quite good. Okay? Yeah. So actually it's here. Okay. So antenna is actually here, but the GPS is showing. So this is the bias. Okay. So precision is very high, but the accuracy is we have some bias. Now to remove this bias, we have to do at least DGPS or RTK or PPP. So if you compare this position with the PPP, maybe this blue dot will come towards the true point. Okay, Abhinav, so thank you very much. So I think we are almost 5 p.m. here, so we are almost near to the break time. So let me stop here. So Abhinav, so okay, so we'll stop here and let me see whether there are additional questions. Okay. Okay, so I think that's okay. So Abhinav, can you stop sharing and then let me share. Let me see what we have in the schedule. Okay, let me share my. So this is actually we missed this one, but we'll have some time over here. Okay, so let me stop here. Okay. Or do you have any questions related with the data processing? And before I stop, so we'll stop after 10 minutes. So before I stop, how many of you would like to present today? Any of you would like to present or not? If none, so we can do more some data processing, or I can show you more such data processing thing, because we want to make you more used to with the data processing rather than the theories, the mathematics and so on. So how to process the data itself. We have 24 hours data and so on. So may I know how many of you would like to make a presentation with what you did? Can you send the message in the chat? If you want to present, please send that you want. Please inform us that you want to present in the chat. Then we know how many of you will be there.
Hello, Dinesh.
Dr. Ize send some information. So we have to download some of these files for PPP, and these files for PPP is for RTK. In RTK we can do PPP, but the PPP that I'm showing today, the Madoka Ppp, our app, we don't need to download all these files. I think we need the antenna file and the DCB file. Okay, let me just show you those files that you need to download, which are let me share one file. Okay. I think you can see my folder. Can you see my folder? So this one is generated. This Madoka is our executive file. And this file you have to download from the, I think we know where from where I think I can get you. Okay, this is a code differential bias for GPS between P1 and C1. Okay, so this is already too old. I think I need to download the new one. So this file you need to download from internet. So this is one requirement. This is the DCB file called bias file, and then also you need the antenna file. Where is that? Yes, this is the antenna file. Okay, so this antenna file, ATX file, is it has an antenna phase center variation, because yesterday I'm telling you that the antenna is quite big. Okay, maybe 5 centimeter or 10 centimeter diameter antenna, but using a 5 or 10 centimeter antenna, big antenna, you are now computing 2 centimeter. So you really need to know where are these electrical waves actually entering the antenna device. Okay, so we call it the phase center of the antenna. So every good antenna, they have a documentation or information comes with the antenna to tell you where is the phase center. So this will tell you how many millimeters or centimeter off from the center of the antenna, the X, Y, and also the Z for every frequency, L1, L2, L5, and L6. So if you buy a good antenna, you will have that type of information. Okay, that is the phase center. But this phase center varies with respect to the elevation of the satellite, because the satellites are moving. So azimuth and elevation. So it's moving around 360 degrees, and also it's moving going up and down. So azimuth and elevation is changing. So as azimuth and elevation of the satellite changes with respect to the antenna, the phase center changes a little bit. Okay, so that's the phase center variation. So how much is that phase center variation? That data is available for many standard antennas. So you have to use this type of good antenna. Okay. And this data is available for different manufacturers from this type of website. For PPP, we need this PCV data, antenna data, for the receiver as well as for the satellite. So every satellite, like this GPS Block 2A, like satellite number 18. So we know the phase center. Okay. Yeah. Okay. The phase center variation, we have it. Although it's very small, but it makes a difference when we are computing at a millimeter or centimeter level. So you must have this type of antenna variation data, both for the satellite and also for the receiver. You see, for GLONASS, you have all this type of data available. Okay. And if you go for receiver, so these are for the receivers, because some receivers, they have a choke ring and some they don't have. So receivers with choke ring and without choke ring. So again, it's a little bit different. So we can see some example. Okay. And these are the PCB data. So we need this type of antenna data, but this we can download. And for the receiver, so if you don't have your for the receiver antenna, if your antenna is not listed in this database, so you can't do anything. So you just use some standard value. So this is what we are doing, because we are using an antenna that is not a very standard one. We're just using the some low cost, but this will not give you a very high accuracy. But at the moment, we have no other way. So we are just using the available antenna, but using one of the default this PCB data instead of keeping it 0. So it has some observation error, but that's the best we can do at the moment. Okay, so this is about some requirements you need. So at least the antenna file and the DCV file that you have to prepare, you need to download from time to time. And that's all for Madoka PPP, and the rest we have in our software. Okay, and if you want to do for PPP in Rtk Live, then also you need to download many other files. Okay, so that's all from me now, and we will break here, and we'll break. But I think Patrick and Shafa from ICZ, I think they have some message to you. So I hand over to ICZ now.
Yeah, thank you, Gnss. Not really anything at this point. So we will resume in 1 hour. If you would, we would just appreciate if you could, during this break, complete the feedback questionnaire. And again, send us message in chat whether you would like to present some of your results, which you perhaps would be able to process and show. If not, then we will just continue our agenda as it is without those presentations. That's perhaps it. Unless Patrick would like to say any words.
No, thanks. No, I think you covered everything. Thanks.
All right. Well, thank you very much, everyone. Have a good time, and we'll see you in an hour.
Mm-hmm. Okay. Thank you.
Hello, everyone. We will continue our sessions. Thank you again for joining us for our last day of the workshop. And I would like to give floor again to Gnss, who will continue the session. And also, I don't see anyone in chat, at least proposing any presentation. And then I haven't received any email either. I don't know about Gnss. So Gnss, The floor is yours.
Okay, so nobody wants to do any presentations. So I wonder whether they could use RTK leaf, or we are not very good enough to give enough instructions. Okay, let me show the data, the Madoka data that we logged and processed. Where is it? RTK plot, okay. Can you see the this graph?
Not yet, Gnss.
Not yet. Okay, what happened? Wait. This is strange. RTK plot. How about now? Can you see some graph, some screen?
Not yet, Gnss.
No.
No.
I don't know why. Okay. So let me share the whole screen then. So now you can see.
Yes, we see your screen.
Okay.
And see the graph.
Okay. So this graph, which you are seeing, is the Madoka that I did the processing before when I was explaining the demo. So let me put the position data. You see here. Okay. Okay, so this is for the east-west, north-south, and up-down. Okay, so this is actually this two horizontal, and this is the vertical accuracy. So if you look at this, so in the beginning, the Madoka, it takes some this convergence time, and this you see the time, so 7:25, 7:30, and as it goes on, so it becomes more stable here. But if you zoom it, so you will see 2 centimeter level of zoom. Okay, so this is how it looks like. Okay, sorry, wait. And I can do, you see, this is how the error fluctuates. Okay, so as we go on, as we observe for more time, this is about more than 1 hour, so it becomes more stable, but it seems to be stable here, but still we have this variation. Okay, so I don't know why this is so here about 5 centimeter. Okay, so the accuracy of this Madoka is not the centimeter level, it's about 20 centimeter. Okay, So we cannot expect 5 centimeter or 2 centimeter of accuracy. This is about 20 centimeter, 10 to 20 centimeter, depending upon your location and also the surrounding conditions. Okay. So this is how it looks like. Okay. So this is what I wanted to show. And if I look at the scatter plot, okay, so again, I will show you. Let me show. So this is my start point. So if I show this, okay, now this scale is a 20 centimeter accuracy. Okay, so by looking this, so this is within 20 centimeter. Okay, so we can say that by doing this, we can have accuracy of about 20 centimeter of grid. Okay. You see how it is moving within this 20 centimeter. But if I zoom it, make it a smaller grid, like a 5 centimeter or 2 centimeter, okay, it's going here and there. Okay. But the total accuracy, so we can guarantee, I think, about 20 centimeter of accuracy. So if 20 centimeter or 10 centimeter, I mean, I can't say 10 centimeter, but 20 centimeter or around 30 centimeter accuracy is good enough for your application. This Madoka Ppp is a good choice. You don't need a base station, but you just need to access the correction data. So this is how the data looks like. But you do have to wait for maybe 20 minutes like that. Otherwise, if you don't, so you will still have this type of error. Okay. So this is one thing. And the next one, so yesterday I got permission from Thailand, from NIMT, National Institute of Meteorology. Now I'm accessing their receiver to get the real-time data. So this is the data from Thailand. Now what I'm doing is I'm accessing a receiver in Thailand and doing a sort of PPP just to test the PPP. And this is the accuracy we can get, okay? So the Thailand, the altitude now, because Thailand's area is below the mean sea level. Okay? Or almost 0 meter. So this is the height value. So this is, so let's forget about the altitude for the time being. So X and Y is this.
Sorry, Dinesh. Sorry,
yeah.
Dinesh, could you please enlarge that window a little bit so that we can read it as well?
Oh, it's, I think, not possible, this window.
Okay. All right.
So the size is the same, okay? The text doesn't, okay. It doesn't, the text size doesn't change.
Okay, all right, thanks.
If I may suggest,
yeah, I see it now.
Maybe increasing the resolution of the screen might help.
Let me try. Let me see this one. Okay, this is a little bit better, but is it better? But but some information may be not visible then. Is it better at your side?
Well, not that much. Okay, it's okay.
Or what I can do is, wait, what I can do is, let me try like this. What I can do is, I can put on the PowerPoint slide and then zoom it, but this will be...
Yeah, perhaps in that case it would be better.
Is it now?
No, it's the same screen now. You haven't changed it yet. At least we don't see.
No, can you see my PowerPoint now?
No.
No?
It's just your desktop.
Oh. Wait. Can you see my PowerPoint?
Yes.
Okay, so what I did is I just screen copy to PowerPoint. Probably you can see the bigger now.
Yeah, we see that. At least we can read all the items there. Yes.
Yes, so but you don't see the real-time working now. Okay, I just made
we don't
a
see.
screen capture.
Yeah.
Okay, but anyways, this is what I can do at the moment. So you see so many satellites here. So this station is in Thailand at the moment. So I am accessing remotely the receiver in Thailand, and I'm giving the QGIS correction data from here in Tokyo. So QGIS data is coming from Tokyo. The receiver is actually in Thailand, and I'm pulling the data from Thailand to my computer in Tokyo and doing the Madoka Ppp. So we can do this software allows you to do this type of a remote, real-time processing. And you can see the accuracy of this processing. Maybe this is not good enough at the moment. Okay, so this will be about 0.5 meter of accuracy at the moment, okay, but it has a capability to do this. So for example, if I can access a receiver in Africa or Brazil, South America, or Europe, or another location, we can do the same. So we can access the receiver in that region, and we can use the correction data, online correction data, to correct the observation in other country in real time. And then we can get a PPP solution in real time. Yeah. So this is the one capability of Madoka PPP. I think the similar capability will be available from Galileo as well. So on day one, we heard from Dominic that they also provide online correction services. So if they provide, then we can do something like this. So this is the one thing that we can do with the Madoka PPP. So it's not necessary that you have to see QGIS satellite. Even if you don't, you can do the high accuracy positioning by using the correction data. So this is the demo, actually accessing the receiver in Thailand. And then so what else we shall do then? Okay, this is for Thailand. So I don't get any other information from the participants to access the receiver data. So I can't make other demos. So this is the one I can do. I can access some of our servers in Asia, but not from Madoka. Okay. So that's all from my demo. And now I would like to discuss with you more this data processing. So why don't you try RTK Live data processing in your computer, those who can do it. If you have a software in your computer, please do the data processing and let me know, or let us know, because now we still have our resource persons from TUMSAT. They are still here, I suppose, to help you answer your questions on data processing. Okay, so let me show you one more that I have not done, or I almost forgot to share this information to you. But it was, I think we have Renato here. I think he gave some information about this as well. Okay. So in the low-cost receiver system, I did not I did not cover Android raw data measurement. So we basically focus on the receiver systems and the RTK leaf data processing. But since we have some time now, I would like to cover a little bit about this, and probably it will be useful for you as well. So let me cover this. So many of you already know that we can use the Android device, because some Android device, they have a GPS chipset that can output the raw data. Raw data means code phase data or code and carrier phase data with the navigation message. Okay. So this was actually the API in Google was done by Dr. Frank and his team. And it was first implemented in the Xiaomi, the Mi 8 mobile phone, and then later many other mobile phones, they have this chipset. And these days also Qualcomm chipset, they are capable to output the raw data. And some mobile phones, the new one, like the one available in the Redmi, Xiaomi Redmi, also in India. So it's capable to also use the Navic data, L1, L5, so dual frequency. But I think they output only the code phase data, not the carrier phase data. So you can't do the RTK, but you can do the DGPS using the internal GPS receiver. But basically what you have to do is look at the raw data, and there are different tools to log this data. And this training material, actually these notes I got from Dr. Frank directly. So while he was doing this training, so I asked for his permission to use, and he gave me all his notes. But these are quite old, in 2019, and you can find the latest these notes in the Galileo, this raw data task force. There is one task force, so also I'm one of the members of that. And on day one, Renato, so our colleague from Croatia, he also shared some information. So please look at the Galileo, this raw data measurement website. You can search, or I think I have a link somewhere. But to do that, you have to use some of the location APIs, and there are basically two types. One is the standard location APIs of the Google, so which are already there. And then this is the new location APIs that is added to provide you the raw data. Okay, these were available in the past already, but these are the new. So Android location, and there are many more coming up. Okay. So this is a little bit old slide, so please check the Google homepage to find out all these new APIs. So you see this GNSS measurement. These are the new APIs that can output the raw data. So raw data means code phase and carrier phase data for RTK. So if you can write or do some programming work, you can use the internal this data to do your own carrier phase measurement or RTK. But at least you can do the DGPS with this. Okay. So these are all the related information. So I'll make a separate this presentation file and then send to ICG website so that you can download as a reference. But this file is a bit old, so I did not modify it. So it's, I think, about more than 1 year. So if you need to find out, so please check the references given here. So if you go to these references, you can find out the latest information here. Okay. And this also old, so don't rely on this table, but at least if you have, or if you can find one of these mobile phones, so they can output the raw data, and which mobile phones are good is listed here, but this is already old and this is no more available in the market. So if you can find some second-hand used Xiaomi Mi 8, so please try to purchase. This is a quite good phone. I'm still using it. So it can output all the raw data, navigation data, everything except the AGC data. This one is not available. Antenna gain, auto gain control data, but all other informations are available. Okay. And if you want to log the raw data from Android devices, so you need some special app. And please check the Galileo homepage. They do lots of competitions every year. So more and more new apps are coming up to log this data. So I use a GNSS logger to log the raw data. So it doesn't output the position data. It just logs all the raw data that outputs by the GNSS chipset inside a mobile phone. Okay, so this GNSS logger data, and this is quite good. Geo++ Rhinox logger. So it will output you the Rhinox observation file. Okay. So N file you can download from any other sources, but it will provide you the O file. So this is good enough for RTK. And this is also dual frequency compatible now. So L1, L2, I think also output the, I don't know about L5, probably it's already L5 compatible as well. And there are other apps developed by this challenge, Galileo challenge, and there are some apps to compare the position data only from L1 or L2 or L5, E1, E5 like that. So based on, you can compute the position only from GPS, you can compute the position only from Galileo, and you can see which one is better. Okay, how they differ, because they differ a little bit due to different types of the satellite orbit data and clock data. So there will be a little bit difference, and you can see this type of differences using this app. I think they probably have the updates on this as well. But when you go to this site, so you'll find more other links. So these are the old files, so please use them if you want to do the Android data logging. So this is the easy way to do this. Okay. And if you use the GNSS logger, so I use this one, so you will see so many satellites. And I'm using the Xiaomi Mi8. So you see how many satellites? 42. So for 39 satellites at this time, but now I can see more than 45. This is about 2 years old data when fewer satellites were there. So now after 2 years, we have more satellites in this space. So we see more satellites here. Okay, and you can select which one you want to see: GPS, SBAS, GLONASS, QZ, Beidou, and Galileo. Okay, so CN0 plot, and you have a lot of control here and see how it's coming up. So you can just download in the Android phone. And even if your Android phone doesn't have a Broadcom chipset of L1, L2, so even if you have other chipset, if it will still output the raw data. You can see something like this, any new Android mobile phone. New means the OS is 7.0 or later. Okay, so you can have this type of thing. The only thing is the output. It differs from chip to chip. I mean, what type of receiver you have inside. The outputs will be different, but this type of plot you can see. And here you can control which one you want to log. The location data, or if you say location, so the output will also have an enemy data output. If you say measurement, so it will output all the raw data, the navigation data bits, and some other conditions. Okay. So these are the file formats. So I don't want to go these details here. So just information what how it looks like. Okay. So it's outputs so many different types of things. So if you are more interested on the signal type and the signal analysis yourself, then this type of information is very, very useful. And this training, I found that there are so many participants who are working on the space weather, ionospheric scintillation, like that. Now, there is one idea using this Android mobile phone, whether this type of raw data is also possible to calculate some of these ionospheric or scintillation, all these space weather related information. So this is a new research topic in using this type of data collected by the Android mobile phone. So if it is possible, so probably we don't have to buy tens of thousands of dollars of receiver. Accuracy may be bad, but if it is possible to collect by Android, then so many people have Android. So you can have crowd sourcing or crowd collection of the data from different location in real time. And then you can send all the data to a server somewhere, and you can do the processing in the server. So you will have more and more data. So if you have more data, probably you can remove the more noise, and you can have a better input probably. So that may be possible. So this is one idea now being discussed, or I think many people are working on this in the Galileo Challenge as well in Europe. So please think about this, whether this is possible or not. I myself is not I don't know much about the space weather or scintillation or atmospheric, so I don't have enough information to do this type of work. So probably those who are doing this scientific or physics related research, so maybe this Android phone with the raw data output is another good option of device to log the data. Okay. So this is how the raw data looks like from this GNSS logger from the Android. And once you log the data, then you can do the post-processing using this software. So you have to download this Gnss Analysis App from the website in here. And this is actually the MATLAB file. So MATLAB compatible files, not a compatible MATLAB files, but compiled for your computer. So you don't need a MATLAB license. So just download, but this file size is quite big, maybe 700 megabyte or near 1 gigabyte. So it takes some time, but once you installation will take a little bit of time. So, and also processing is a bit slow because it's developed in MATLAB, and this is a license free. You don't need a license of MATLAB. You can just download and install in your computer, and you can run it and do the post-processing. And it has lots of this processing capability. And this is a very nice tool to see how the signals are actually processed. Okay, so you can learn. So what is the pseudo range carrier phase, and how the errors in the pseudo range, the carrier phase, and so many different types of raw data analysis. So if you are really interested in a very deep signal analysis, I think this tool is a very, very nice for study. So this is some output of this software. And I was doing some tests in our campus. So this is some tall building. So we have an open area and another building here. And this Xiaomi Mi 8 is actually quite good. So when I do the post-processing, the RTK, so I did RTK, you see it's very nice circle here. Okay, so it doesn't jump here and there. The accuracy is, I think this is a few meters. So this is not the RTK. It's just a standard point positioning in this case. So I don't do the RTK here. Just observe for half an hour or 1 hour and then process. Okay, no DGPS, no RTK, but we can also do the RTK if we want. But in this case, it's not done. Just observe and there. So the good point of this is that there's no scattering, no jumping of the data here and there. Okay, because this is L1 and L5. So when we have L1 and L5, so it's a dual frequency. So the output is much, much better than the single frequency. So you can see this circle. I think this is within the 3 meter or 5 meter of circle. So within the 3 to 5 meter, it's very nice. So other receiver also you get the accuracy of 3 meters like that, but that's you will also see many jumping points. Okay, the scatter points, but this one is very cluttered like this in this open environment. But if I go under the tree, like here's my huge tree. So I intentionally sat under the tree. This is our main campus in Tokyo, the University of Tokyo. This is a famous landmark. And there's a big tree here. You can see the crown. And I sat below the tree to have a very, bad signal. The signals will be attenuated under the tree because it's a microwave. And also you will have some reflections. And then the accuracy is like this, okay, due to the multipath. but still, again, the points don't go here and there. Okay, it doesn't jump much here. So I think it's quite good. And this is near the area. So this is a little bit suburban. So in the agricultural land, so there's no buildings, no multipath here, and this is a 5-meter circle. So if you don't have multipath, so the data is very nice, even from the Android phone. Okay, so my accuracy is, I can guarantee my accuracy is within 5 meters. Okay, so here when there is a multipath, we see this type of a scattering due to the, I mean, not the scattering, but this type of error. So maybe this is a 10 meter or 15 meters of this. But it's elongated like this due to the multipath. But when there's no multipath, it's very circular. Okay, so if you take a mean of this, it's a very nice point data. So this is how it looks like. And this is a data in Australia, Melbourne. So when we had this program in Melbourne near the park, so I was sitting here on a bench here. Again, this is, you see, very cluttered. So we had a data from Tokyo, and then when I went to Australia, Melbourne, so again, I logged the data with the same mobile phone, and again, the accuracy is like this. Okay, so we have a very nice this one, and also there are some trees here. So due to the trees, this thing is a little bit elongated, but nevertheless, it's within the 5 meters of this circle. Okay, so here, actually, I was sitting in this bench, and there are trees like this. And this is another very nice data. So here you can see, so I suppose some of you can recognize this place. So this is the Kennedy Space Center where they launched the SpaceX, the rocket that comes down. So I was there when they were launching one of the rockets, and we were lucky to see the launching. So it actually goes up, and then after some time, so those boosters and rocket, it comes down again, and it's a very nice landing to see. So that was this is the Kennedy Space Center. So I was staying in this hotel, and I have to go to our office every day here. So when I go there, I take a Uber taxi. Okay, so while I go from here to here, I put my Android device on the seat next to me. Okay, I don't put the Android device on the dashboard, or just I put next to me in a taxi inside the car, and we just drive. So you see the data, it's very clean. Okay, we don't see the points jumping here and there. It's very smooth, very nice data, even if the device is inside the car. And that's very amazing how good or how nice is this data. Okay. But the one reason is that in this area in the USA, the roads are very wide and there are no much traffic, and almost it's an open sky. Okay, although the device is inside the car, so I didn't see any problem here, and the data is very nice. So this is driving, so very smooth output, and if I zoom here, you see, okay, very smooth zoom. You really don't see the points jumping here and there. So this shows that the dual frequency receiver, although we don't do DGPS or RTK, even with the standard point positioning, L1 and L5, the accuracy is quite good. So when I'm driving, so when the car is on this route, so it's also follow the exact track. And if I zoom, it doesn't go out of the track of this road. Okay, so this is very nice data. So normally, if you use only L1, when you take a turn, sometimes this data during the turns, it jumps a lot. Okay, you please log this data and see yourself with your Android mobile phone. So you will see a big difference in your data. You won't find this if you use only L1. But here you see there are some points clutter. So we have some traffic jam because during this launching day, so many people are coming to the Space Center. and there are lots of cars waiting for the entrance for security check and all. So we have to wait here for quite some time. But still, while we were waiting, so the points don't jump here and there. Okay? It's almost the same point. And again here, we have to wait. Okay, and then we go to the car park and then we walk. Okay, so it's all the way here and very nice data in the USA. So I tested this in the USA, many countries in Europe, and in Australia, in Japan, and many countries in Asia, Thailand, Indonesia, Philippines, and so many other countries. And wherever I took the data, it's very, very nice. So some of this data I can also share if you want to do the analysis. So these data are available. So, but depending upon your interest, so I can share the data so you can look at it and you can do the processing and so on. We have lots of sample data. Okay, and this is the recent data. So I have a MI8 and oh, this is in the Suva, Fiji. So also in Fiji. So Fiji is again quite far from here. So the same this MI8 device. So accuracy is again within 5 meters. And then this is another device P20. So P20 is also dual frequency L1 and L5. So MI8, and we were comparing the accuracy from two different types of Android device, MI8 and P20. You see, P20 is a little bit worse than MI8. Okay, the scatterings are more here. Okay, this is a MI8. This red is a P20. Okay, so MI8 is better. P20 is a little bit worse in performance. So this is what we see. We put at the same location. Over this ground control point of Fiji Survey Department. And this is from TUMSAT. So Dr. Ije and his team helped me to log the data and walking around and see whether we also get the same track using this Android phone. Okay, so this is from TUMSAT from Dr. Ije. And we are using only GPS L1 or L1 and L5 comparison and all. So only L1 is not so good. So if we combine L1, L5 is a little bit better, but then we combine more. So when we combine more and when we do the RTK, so this is the RTK fix, this is the RTK float. So fix and float solution. So when we combine more, it's better. Of course, that is true, but you see the shape of the track. Okay, I think this is the most accurate track. So you need L1, L5 to have this type of very accurate track. So only L1 doesn't give you good output. So L1, L5 is much better than L1 alone. You see, this is now very straight. Okay, some output. So all these frequency drifts with clock and all clock bias, clock error. So some of you doing this timing and all, maybe this will help you to do all these type of analysis. So also I'm not expert in this clock related things. I don't know much about the space weather, ionospheric scintillations and all. So maybe we have other colleagues who are expert on this, but using this type of device, you can get a lot of raw data and you can do a lot of different types of signal processing. And I think that will be very nice things to learn more about the signal processing. Like our guy from India, he's developing the Android app. So maybe he can take some of these informations as a guideline to improve the accuracy of the GNSS receiver, or try to do maybe built-in receiver to do DGPS output or RTK or whatever. Okay, so this is what we have to do. And this is Geo++ as well. So please download and do all these things yourself and see which is better for your application. So maybe Rtk Droid or maybe this type, or you can do these are just a logger to output the Rtk data. Okay, so it's quite good. Oh, this is our Rtk Droid CSW map, and this is the Galileo task force pages. Okay, Please check this homepage. So they have lots of informations and they have very recent articles. I mean, lots of outputs and so on. Okay, that's all. So I saw a message from Renato. So he has lots of information here. Related with probably this is related with raw data from Android device as well. So, okay, app just collects pseudo range post processing done using Rtk or some other software. Okay. Let me see some questions here. Motorola, OnePlus, Huawei also support Android location API. Yep. And then useful apps, Geo++, Rhinox, Logger, OnePlus, Node operates dual frequency GNSS receiver. A question for international GNSS service. Do you plan to continue the provision of RhinoxP files for multi-GNSS post-processing? But this is a question to IGS service, so I cannot answer that. There is any way to collect raw signals from Android devices? Yes, that's what we explained. So please use one of these apps. So where I can find the document for Madoka Ppp? If you are looking for the technical document of Madoka Ppp, please check the homepage of the QGIS. So I can check that for you. But if you are looking the software manual, so you are saying the user manual for Madoka Ppp, so you have to get first the Madoka Ppp software, and then only the user manual will help you. But our user manual is just 2-3 pages actually, so you don't have much things to set up there. So as I explained during my presentation, so you just need to select which one to use, whether you want to use the directly connected receiver or online receiver. Okay. So please, if you are interested for Madoka, please send a request form. But as I mentioned, for Madoka software, we can give you the software, but for the hardware, we need to have a collaboration agreement. Okay. So please fill up the request form, then you can see the manual and all. But the manual, we don't have much on that. Okay, just a few pages. And from Kyle, hi Dinesh, I'm creating a web app server that observes ionospheric scintillation using raw GNSS data. That is a good idea to incorporate Android phones to observe. Yeah, that I think this is a very good, nice idea, but I'm not sure whether this is actually possible. So theoretically it may be, but in practice, I'm not sure. Maybe Renato has you would need a dual frequency observation for that. Just is several smartphone. Yeah, but even the dual frequency, so we don't know. So unless somebody actually does the processing and share the results, we really don't know whether this is good enough to or not. Okay. So this is now being, many people are doing research on this actually. So maybe this year we'll see more output on that ionospheric from the Android data. Should be possible, should be possible. Will Gnss Analysis App do post-processing for any single or dual frequency data from other receivers also? Of course, yes, this is what we have been talking for the last 2 days. So please use the data exchange format, the Gnss format, so you can do from any other receiver. You can use combination of any receivers, no problem at all. But you have to use a common data format, that's Gnss, to share among the receivers. Using GNSS logger apps, simply we hold the Android device somewhere. Yes, yes. So when you log, so I have one recommendation for logging the GNSS, I mean the Android GNSS data using an Android app. So if you have to know where is the antenna, okay? I suppose that many devices, the GNSS antenna that output the raw device, the antenna is on the screen, just below the screen. So you hold the antenna, you hold the device in such a way that your screen looks the sky. Don't hold the device vertically. I mean, don't face the screen towards your face. So you hold the antenna horizontally. So you hold the device horizontally so that the screen looks the sky. And for MI8, the antenna is just below the screen. Okay, so you have to hold the antenna horizontally. That gives you the best signal possible. If you hold the antenna vertically, still it gets, but maybe not so good. App just collects pseudo ranges. Post processing should be done using RTK leaf, but Renato, but I don't agree with that. I don't know which app you are talking. If you are talking about the GNSS logger app, it's not only pseudo range, it also collects the carrier phase. But probably you are not seeing carrier phase because the device you have is not able to output the carrier phase data then. Because even with the same model, sometimes the chip inside the receiver, I mean the Android device, is different. And there are some models for like a certain country or international version and so on. Sometimes they have a very tricky, this type of models, having a different types of GNSS chipsets. So actually, GNSS logger capture the raw data, but you have to enable in your setting when you log the data. Okay. Several publications outlining, yeah, okay, there are a list of the publications. Very long list. Okay, we have Madoka, we need to register. Yes, of course. Not the register, but please send the request. Okay. Madwin, yeah. Okay, Renato, your microphone is not working, so please send by chat. Any detailed instructions on how to put together the different types of unit? Any detailed instruction on how to put together the different types of units, ABCD? Yeah, this is you use the Gnss for post-processing data format, or if you want to do in real time, you set the RTCM to broadcast the message that you want to do so that you can combine type A with type B for real-time correction. So use the RTCM for real time, or if you want to do the post-processing, convert all the data to Gnss format. And from ISRO, excellent work being done in Japan. Do you have some presentation material on GPS PPP processing using RTK with some sample data? Yes, this we have. So our colleagues from Tokyo University of Marine Science, they have lots of this information. They also have an example on how to do the PPP using RTK leaf. So Dr. Ije and Kaito Kobayashi and Professor Kubo, they can share this information with you. or we can provide send by email, or we can post in our website. So please check, and I'll also keep a note on this. And if necessary, we'll do an online training again in future sometime to only focusing on how to do PPP using RTK Live in future. Okay, that's one good thing. Okay, this is about the publication. Where to study the concept used for PPP, any reference links, documents. Yeah, we have lots of things coming up. Also, we had some references yesterday. So, but I think if you search in the Google Scholar, you see a lot of this. Okay, I myself, I don't collect the PPP this thing because I'm not involved in the development of the PPP itself. But you really find lots of things in this one. So please, best thing is do the Google search. I think that's the, best answer for you. Okay, so there was I think this chat. So Patrick, how are we going to do this QA in the chat? Are you going to list this somewhere? Because in day one, we received some of these PPP related material references. And I think that will be very useful for other participants as well.
So what would you like to do? Share some files or?
No, I mean, we have this QA, question and answers. I mean, the questions coming up in the chat, yeah. But we are not typing the answers. Of course, this video will be available later. So are you going to make a separate this question file from this chat message?
I'm afraid the chat cannot be exported, so we will have the recordings. I think all the questions in the chat were read out loud and replied to. So, but let me have a look if there's any possibility. We tried it once. Might be that the future feature has been added.
I think it's possible to export the chat if you have that access. So as an admin, I think you should be able to do that, but I'm not sure. I'm not sure.
I said in the past we tried once and it did not work, but I'm more than happy to look again. I said Teams is constantly being enhanced, so maybe they have added an option, and then we can share all the information. We can also share the text file of the chat.
Okay. So, and there's one question related to the PPP about the integer ambiguities by resolving PPP. If yes, how initial phase bias and Arnosphere are dealt with? Is it so reliable? Sorry, I don't have a technical answer to this. I'm not the expert on the PPP. So I don't know whether our colleagues from TUMSAT, Dr. Ize, are you still with us? Maybe I need to ask your question to our expert who developed the PPP software. I need to ask him how it is implemented internally. Are there studies on the PCV antenna calibration of Xiaomi or other Android phone? Yes, I think this is, please check the Galileo homepage, so you can find the very nice PCV calibration data. I think this was published in the last year's workshop, so you can find it in the Galileo raw data measurement workshop. It's a very nice data available there. What I need to be able to use Madoka in the north of Africa. So please register to the link that I gave to you. Then I will send you the software. So please try with the software first. And then if it is okay, then we can see how we can send the device to you. Okay, so this from, okay, the last question, I think. Okay, so that's all the questions, and there are 2 or 3 questions that I cannot answer. Okay, that's all from me. So, any other questions? Okay, so I would like to stop here and hand over to our colleagues at the ICG. So thank you very much.
Thank you. Thank you, Dinesh. Well, in accordance with our program, we basically came to the concluding remarks, and I would like on behalf of our office and my colleague Patrick to thank you, all the presenters and all of you attendees who stayed with us throughout these 3 days. We hope it was very useful for you, and we appreciate your time and contributions you made through your questions and your emails you were sending to us. Well, thank you very much once again. Please complete our feedback questionnaire if you haven't done so. We will, as we said at the beginning of the workshop, that everything is recorded, and after editing, it would be put onto the YouTube channel of our office, and we will provide you link to that. Also, as you know, all the presentations are already made available on our website. Please check them out. The last slides, which Dinesh just showed right now, today, we will also post it onto the website, so please check for the availability. With that, once again, thank you very much. And Dinesh, would you like to say a few words? So please, the floor is yours, and with that we can conclude our workshop. Please, Dinesh.
Okay, so first of all, I would like to thank all of you who participated this training course. So as I mentioned on day 1, that actually this is supposed to be held in Thailand every year in January, or physical this training. So we used to have a very huge team, and with the hands-on, you actually going out into the field, doing all the tests and all. But unfortunately, we could not do this this time. So instead giving up everything, so at least we want to give the information that what we can do and how it can be done. So this objective of this training is to provide you at least some information on how we can do the data processing using these low-cost receivers and system, and to tell you what type of software we have, because hardware you can purchase, but software is always a problem. So we have customized the software so that you can use for your various applications and all. So that's one thing. So after this training, so we strongly recommend you to do the data analysis if you are interested to do that for the technology promotion in your country, in your working place, and so on. And you can contact us anytime, just send an email. Also, I have given some other references, links, website. Also, I have created a Facebook page only for this, basically not only, but basically for GNS related activities, that all the programs we have, trainings, webinars, seminars, or something new coming up, new informations or new data. So I always upload in my Facebook that is created for GNSS. So if you register there, you can get those information. But everybody doesn't like that one, so you can send an email or just contact, or you better look our homepage time to time, ICG homepage or my homepage or university homepage. So that's one area for the follow-up. So this follow-up is very important if you want to continue your research or your work, or either it is commercial or non-commercial, so we don't care. But as long as it's related with GNSS, so we can support. Okay. And the other thing is that so we need your evaluation because this COVID situation, I don't think it will improve very soon. It may be the same even next year. So what to do in the next half year or 1 year? So whether probably we need to do this type of online training again in the next even in the next half year. So if we have to do online, so whether this is effective or not, and how do you want to do this? We thought maybe you will be doing the all these exercise at after the training and all, and maybe presenting some of your work today, even for a few slides, few minutes. But it seems that it's a little bit difficult to do that. Okay, but I don't know. You are also not get used to with this, and also we are participating from the different parts of the world, and the time difference, and also the internet problem, and also the language problem. So I don't know whether the my talk you can understand or not. So it's all the problems exist, but besides that, we want to continue. So that's all. And the last information is that, so from the university, we want to extend our network to more countries in the coming year. So basically the universities or research organization or government organization, so those who are interested, so please contact us for the future collaboration as well. So with this, I would like to thank you all, and I will stop here. So thank you very much. And also I would like to thank ICG to provide all these logistics for online and all, doing all these applications and a lot of very difficult tasks. So thank you very much.
Thank you, Dinesh. And again, thank you all. With that, we conclude our workshop.
Finally, I would like to thank all our resource persons from Europe, Japan, and from TUMSAT. So I don't think all of them are present today, but without them, we cannot do this workshop. And we have so many people to help you to give this information, and they really spend a lot of time to prepare themselves and keeping awake at early morning or late night, so on. So please look at those resources because they spend a lot of time as well. So that's all. Thank you.
Thank you again, Dinesh. Not all the presenters are today at this workshop, at today's session, but they really were very interested from the beginning when they accepted our invitation to contribute to this workshop, and they willing also to take your questions if you have any and didn't have a chance to ask them. So you can always write to me or to Patrick, and we will be happy to forward them to our experts. Well, again, thank you very much. Wishing you all a good day or good evening, good night. Bye.
Yeah, thank you. Bye-bye.